last lecture I have introduced certain characteristics of the probability distributions, such as its expected value, that is the mean, variance, and also some higher order moments. So, the mean of the variance distribution denotes the measure of central tendency or the measure of location for a distribution. The variance or the standard deviation denote the they tell the about the variability of the values of the distribution. We may also be interested in some further characteristics of the probability distribution, such as its skewness. Let us define what is an skewness. So, consider a distribution of this type. Let us consider another distribution, and let us consider now, if we compare the shape of the curves, the first reaction after looking at the first curve is that it is symmetric about a certain axis, say mu. If we look at the second curve, then there is lot of concentration of probability on the left hand side and there is a long tail on the right side. That means, there is a long tail to the right of the mean of the distribution. Whereas, if we look at the third curve here, then there is a long tail to the left, and that means there are more concentration of values on the right side and there is a large variation towards the left of the mean. So, we will call this as a symmetric curve. We considered the definition of symmetric distribution earlier, that is probability that x is less than or equal to x is equal to probability x greater than or equal to x for a certain, suppose if it is symmetric about 0, then we should have this kind of thing. So, if it is not symmetric, we will call it skewed. So, this one will be called positively skewed and this one we will call as negatively skewed distribution. A measure for this can be defined in terms of, say, let me call it beta 1, that is equal to mu 3 divided by mu 2 to the power 3 by 2. We are considering this division by mu 2 to the power 3 by 2, that is sigma cube, where sigma denotes the standard deviation of a distribution. This is to make it free from the units of measurement. So, if beta 1 is 0, we have symmetry. If it is greater than 0, it is positively skewed. If it is less than 0, it is negatively skewed. We also define another characteristic called peakedness of a distribution. Compare the curves . So, if we look at it, this has a high peak, this is somewhat in the middle or average or normal, and this is more flat curve. We consider this property as the kurtosis. So, this we call as a normal peak, this is called leptokurtic, that is high peak, and this is called platykurtic, that is the flat peak. A measure of kurtosis or peakedness is defined to be beta 2 is equal to mu 4 by mu 2 square minus 3. So, if it is 0, we have a normal peak. If it is greater than 0, it is leptokurtic, and if it is less than 0, we call it platykurtic. The peak of a normal distribution, which will be defined later on, that will have the coefficient beta 2 is equal to 0. So, peak of any distribution is actually compared with the peak of a normal distribution. Now, we have already seen that sometimes moments of the distributions may not exist. or a lower order moment may exist, but higher order moments may not exist. We have a general result in this direction. If the moment of order say t, where t is greater than 0 exists, then the moment of order s, where 0 is less than s is less than t, exists for a given random variable x. So, if a positive ordered moment exists, then all lower ordered positive moments will exist for the given random variable. Let us look at the proof of this one. For convenience, let me take x to be a continuous random variable. Let x be a continuous random variable with say probability density function f x. Let us write down expectation of modulus x to the power s. This is equal to integral minus infinity to infinity modulus x to the power s f x dx. This one we split into two regions, modulus x less than or equal to 1 and modulus x greater than 1. In this region where modulus x is less than or equal to 1, I can replace this by 1. So, this is less than or equal to integral of modulus x less than or equal to 1 f x dx, which is nothing but the probability that modulus x is less than or equal to 1. When modulus x is greater than 1, if I replace this power s by power t, I will get a bigger quantity. So, this becomes modulus x to the power t f x dx. Now, this is less than the expectation of modulus. So, the first term itself, this is less than or equal to 1 and this is less than expectation of modulus x to the power t. Since we are assuming that the moment of order t exists, this is finite and therefore, expectation of modulus x to the power s is finite. That means, the moment of order s exists. This is the condition for existence of the moment of order s. Now, sometimes when the moments do not exist, then it may be difficult to find out the measures of central tendency or measure of location or measure of variability or say measure of symmetry or kurtosis, etc. So, we may look at the points on the distribution itself, which divide the curve into certain regions with certain proportions. These are called quantiles of the distribution. To explain the concept, let us consider some distribution with a particular shape. Suppose I have a point here, let us call it say A, and if I say probability that x is less than or equal to A is equal to p, that means this weightage is p and this weightage is 1 minus p, then this A is called the pth quantile. It is easy to explain the concept of median, for example, that it divides the distribution into two parts, the probability is half in this portion, the probability is half in this portion. So, roughly speaking, a pth quantile is the point up to which the probability of random variable taking a value is p and the probability beyond that is 1 minus p. However, to take care of the discrete distributions, we give the formal definition of a quantile as follows: a number, let me call it q p, satisfying probability x less than or equal to q p greater than or equal to p and probability x greater than or equal to q p greater than or equal to 1 minus p for 0 less than p less than 1 is called pth quantile or quantile of order p of the distribution of x. So, obviously, if f is absolutely continuous distribution function, then you will have f of q p is equal to p. That is, there will be a unique quantile. So, q half is called median of x, we use a notation m. Also q 1 by 4, q half and q 3 by 4, these are called quartiles of x. We also define say q 1 by 10, q 2 by 10 and so on, q 9 by 10 etcetera. These are called deciles. You can write q 1 by 100, q 2 by 100 and so on. These are called percentiles. That means, if we want to divide the distribution into 10 parts, the distribution into 4 parts, the distribution into 100 parts etcetera. So, they are having different notations. In various problems, we are interested in different kind of quantiles. For example, in various studies, we may be interested in percentage of the people living below poverty line etcetera. So, this is some particular percentile, but suppose we say 25% people lie below a certain thing or 75% of the items are above something, then it becomes quartiles. Let us explain through certain examples. Let us consider f x is equal to 1 by pi 1 by 1 plus x square minus infinity less than x less than infinity. We have seen that for this distribution the mean does not exist. Therefore, there is no question of higher order moments also existing. However, if we look at f x, then it is equal to 1 by pi tan inverse x minus pi by 2, and if we calculate this is plus pi by 2. So, if we calculate say the point f x m is equal to half, then this is corresponding to simply x or m is equal to half, m is equal to 0, which is clear if we plot this distribution. So, it is symmetric about the point 0. So, if the distribution is symmetric about a given point, then that point will be actually the median of the distribution. We can also calculate the quartiles here. Suppose we look at f x q 1 is equal to 1 by 4, then this gives 1 by pi tan inverse x plus pi by 2 is equal to 1 by 4. This means tan inverse x is equal to minus pi by 4, that means x is equal to minus 1. Similarly, if I calculate, so this is q 1, that is the first quartile in this distribution is minus 1, second quartile that is median is 0, and a similar way if I look at f x q 3 is equal to 1 by 4, 3 by 4, then this will give me q 3 is equal to plus 1. So, we are able to determine the measures on the curve. So, it roughly tells that 25% of the observations lie below -1, 25% of the observations lie between -1 and 0, 25% of the observations lie between 0 and 1, and 25% of the observations lie beyond 1. So, it has a very long tail, because in fact 50% of the probability is between -1 to 1, and rest 50% is dispersed over -infinity to -1 and 1 to infinity. Let us consider, say, probability x is equal to -2 and probability x is equal to 0 is, say, 1 by 4. Probability, say, x is equal to 1 is equal to, say, 1 by 3, and probability x equal to 2 is, suppose, 1 by 6. So, this is a discrete distribution concentrated on 4 points -2, 0, 1 and 2. So, if we apply the definition of the median, probability x less than or equal to m is greater than or equal to half, and probability x greater than or equal to m is also greater than or equal to half. So, median must satisfy this condition. So, you look at which points satisfy this condition. Now, here the probability of x being less than or equal to 0 is half, because probability of x equal to -2 and probability x equal to 0 both are 1 by 4. So, as soon as we approach 0, if we look at the up to at -2 you have 1 by 4, at 0 you have 1 by 4, at 1 you have 1 by 3, and at 2 you have 1 by 6. So, any point after 0, this will have the condition probability x less than or equal to m greater than or equal to half satisfied. If we look at the second condition, here the probability is 1 by 3, here the probability is 1 by 6 and 1 by 3. So, if you add, this becomes half. So, if I consider m to be any point before 1, then probability that x greater than or equal to m is greater than or equal to half is satisfied. In fact, if I consider probability x greater than or equal to 1, then it is equal to probability x plus x equal to 1 plus probability x equal to 2, which is equal to half. So, any point which is less than or equal to 1 will satisfy the second condition. Any point which is greater than or equal to 0 will satisfy the first condition. So, any m such that 0 less than or equal to m less than or equal to 1 satisfies the two conditions. Hence, m belonging to 0 to 1 is a median. So, this is a case where the median is not unique. So, in particular in discrete distributions, we may not have a unique quantile. In the continuous random variable case, there will be a unique quantile. There is another function called moment generating function, which tells something about the distribution. So, let us consider that. Let x be a random variable. The function m x at t is defined to be expectation of e to the power t x is called moment generating function. of the random variable x, provided it exists, provided the right hand side exists for some t not equal to 0. As you can see here, at t is equal to 0, this will always exist. So, for t not equal to 0, it should exist, that means, in a neighborhood of the origin, if it exists, then we say that the moment generating function is well defined. We may have a case that moment generating function may not exist. Let us consider. Suppose you take f x is equal to 1 by pi 1 by 1 plus x square. So, if I look at expectation of e to the power t x, then it is equal to minus infinity to infinity 1 by pi 1 by 1 plus x square e to the power t x dx. So, if you look at this one, then this does not always exist, because in the numerator you have a exponential term and in the denominator you have only polynomial. In fact, we have seen that the mean itself does not exist. That means, if I put here x in place of e to the power t x, that itself does not exist. For t not equal to 0. Let us take another example. Say f x is equal to half e to the power minus x by 2 for x greater than 0, 0 for x less than or equal to 0. Let us consider m x t. So, it is equal to integral 0 to infinity half e to the power t x e to the power minus x by 2 dx. Now, this you can combine. So, it becomes 0 to infinity half e to the power minus half 1 minus 2 t x dx, that is equal to 1 by 1 minus 2 t for t less than half. So, here the moment generating function exists in a neighborhood of 0. The point that why we are interested in a function called moment generating function is that it gives, first of all, it uniquely determines a distribution. Also, it gives lot of information about the moments. That is why the name moment generating function is there. Let us look at that thing. So, we have the following result. The moment generating function uniquely determines a CDF, and conversely, if the moment generating function exists, it is unique. If the moment generating function m x t exists for modulus t less than t naught, that means, in a neighborhood of 0, the derivatives of all orders exist at t equal to 0 and can be evaluated under the integral sign. Integral sign, or you can say summation sign, depending upon whether the discrete or continuous distribution is there. So, derivative of the moment generating function of order k at t equal to 0 gives you the kth non central moment. That is why it is known as a moment generating function. You can see this fact. If I say that the moment generating function exists, then I can consider the expansion of e to the power t x in a Maclaurin series as 1 plus t x by 1 factorial t x square by 2 factorial and so on. This is equal to 1 plus t by 1 factorial mu 1 prime t square by 2 factorial mu 2 prime, etcetera. That means, coefficient of t to the power k by k factorial is the kth order non central moment for k equal to 1, 2 and so on. Let us consider this example where m x t is equal to 1 divided by 1 minus 2 t. For t less than half. Let us consider derivative of this. So, that is equal to minus 1 by 1 minus 2 t square, then minus. So, it becomes plus and then you are multiplying 2. You put t equal to 0 here, that is equal to 1 by 4 and 2. So, it is half. Let us check here directly from the distribution. If I calculate expectation of x, this is equal to integral x by 2 e to the power minus x by 2 dx 0 to infinity. So, if we integrate this by parts or if we use the gamma function, then it is gamma 2 divided by this is 2 here. So, you will get 2, that is equal to 1 by 2 square and then this is this will be 2 here, 1 by 1 minus 2 t whole square and then you have 2 here. Let mu k prime be the moment sequence of random variable x if the series sigma mu k prime by k factorial t to the power k converges absolutely for some t greater than 0, then mu k prime uniquely determines the CDF f of the random variable x. That is all in today's lecture.